In this video, I'm going to go through the various representations for the equation of a straight line in R2. So let's think of this example here, the general equation 3x plus y equals 6, which is represented by this diagram on the left. It's the line L passing through the point x equals 2, y equals 0, and x equals 0, y equals 6. The slope-intercept form for this line, the way we get that is to write y on the left-hand side equals, and then a number called the slope times x plus another number. So if we rearrange the general equation and leave y on the left-hand side and move the 3x to the right-hand side, it will become minus 3x on the right-hand side, so the slope is minus 3, and then the intercept here is 6. So that's the slope-intercept form of the equation. The next form that I want to talk about is the normal form, and for that we need a vector n called the normal vector and a point P. The point P is just an arbitrary point along the line. Doesn't matter where you put it, but for convenience let's put it at 1, 3. Then the normal vector is the perpendicular coming away from the point P at a right angle to the line, and for every 3 we go in the x direction, we would go 1 in the y direction. So the normal vector here is 3, 1. So let's write out what that looks like in this case for the normal form of the equation of the line. So we're going to have n 3, 1 dot product with x, and x now is a vector, so it's x, y. So x, y equals, and then normal vector again, 3, 1 dot product this time with the point P, which in vector form is 1, 3. And if I expand this, I'm going to have 3x plus y on the left hand side, and then on the right hand side I'll have 3 times 1 plus 1 times 3, so I'll have 6. So we can see we're back to the general equation of the line. Next, let's think about the vector form of the equation. So we're going to use the point P again, and now we're going to use a vector D, which is called the direction vector. So starting from point P, if we move along the line, for every 1 in the x direction, we're going to go minus 3 in the y direction, so the direction vector is 1, minus 3. So let's write out what that looks like. So the vector x, so xy equals point P, so 1, 3, plus t, which is just a scalar, and the direction vector d, 1, minus 3. So if I break that out into its components, we get what are called the parametric equations. So x, component x will be 1 plus t, and component y is going to be 3 minus 3t. So these are the parametric equations. So one thing you might have noticed when we did all this was, why did I pick 1, 3 for the point? I could have picked anywhere along the line. And why, when I came perpendicular to the line, did I go in this direction and not in the opposite direction? And also, when I picked the direction vector d, why did I go down this way instead of up this way? So let's see what happens if we change some of those decisions. What happens first if we move point P to 2, 0? Let's look at the normal form of the equation first. So we're going to stick with 3, 1 as the vector n, but we'll just move the point P. So we're going to have this as our normal form. So all that's changed is the point P. Let's multiply this out. We're going to have 3 times 2 plus 1 times 0, so we're going to have 6. So we're back where we were to begin with. So moving the point P doesn't change the normal form of the equation. What about the vector form? Does that change? Well, let's have a look. So we got xy equals P, so let's move P to 2, 0, plus T times the direction vector, which is 1 minus 3. So remember, T is just a scalar, so I could shift that scalar. For example, if I shifted it to let's say S minus 1. Okay, whether I use S or whether I use T, it doesn't really matter. So let's shift it to S minus 1. So now I'm going to have 2, 0 plus S minus 1 times 1 minus 3. And so if I collect the constant part of this vector here, I'll have 2, 0 plus minus 1 times 1 minus 3. So I'm going to have, let's write it down here, I have 2 minus 1 for the x component, and then I'll have 0 plus minus 1 times minus 3. I'll have 1, 3. Plus s times 1 minus 3. Okay, so I've got the same vector form as I had before. Here I had before, when I had point P equal to 1, 3, I've got xy equals 1, 3 plus t times 1 minus 3. And now when I moved point P to 2, 0, I've got 1, 3 plus s times 1 minus 3. Remember, s and t, they're just scalars. So whether I use t or whether I use s doesn't matter. The vector form is the same. Okay, let's do a similar process, changing the normal vector. See what happens. So in this case, let's look at the normal form of the equation. So this time I've got minus 3 minus 1 dot product xy equals minus 3 minus 1 dot product. And let's move back to having P at 1, 3. If I just multiply both sides of this equation by minus 1, that's going to be equivalent to 3, 1 dot product xy equals 3, 1 dot product 1, 3. So we're back where we started. So changing the normal vector, so it points in the opposite direction, doesn't make any difference. And finally, let's change the direction vector to minus 1, 3. So let's look at the vector form of the equation this time. And what do we have? So we got xy equals P. So we're back to 1, 3 for P, plus a scalar t times the direction vector minus 1, 3. And this time let's have t equals minus s. So I'll rewrite this as 1, 3 minus s minus 1, 3. And let's just rewrite that. So we've got a positive here. So 1, 3 plus s 1 minus 3. Okay, and we're back to where we started again. So the same vector form as we had before. So, in summary, there's various ways of writing the equation of a line in R2. We have the general equation, We have the slope-intercept form, we have the normal form, we have the vector form. When you're writing equations in the normal form or the vector form, you have to pick a point P and a normal vector and a direction vector, and there's a certain amount of arbitrariness around how you pick those, but as we've seen, it doesn't really matter. So point P and normal vector and direction vectors are picked for convenience, and often they're picked in a way that makes the resulting normal form or vector form as simple as possible.